Good afternoon, first of all. This work I'll be presenting is work I'm doing as part of my master's degree, as Diego said. It's partially funded by ICT4B. It's a research center in Uruguay that was an initiative of Daniel Kaufman with a series of enterprises in the country, and, well, I'm doing it at my university, Universidad, Uruguay. First of all, just to give a brief outline about what I'll be talking about. Our main motivation is Explainable AI, so I'll give a little explanation of it. Then I'll define our problem. I'll tell you a little bit about regular inference. That's our main methodology. Then our contribution, a concrete application example, and then some conclusions and future work. First of all, what's Explainable AI? Well, nowadays we are having these huge developments in AI. We are achieving performances that are over human level in image classification, natural language processing. We are getting good classifiers. Classifiers we do not clearly understand. They manage to have good performance metrics, but the interpretability of those models is not good. We understand how the computation is done, but we do not understand why the computation ends up with such results. So DARPA proposes a lot of definitions for this, and they mention that, well, there are many applications where it is interesting to know what happened. Why the system is telling me, for example, that a transaction is risky. Why the system is telling me that this patient has this disease. Because a doctor cannot tell you, okay, you have cancer. Trust me, you have cancer because this black box model is quite good at detecting people with cancer. But why, doctor? I don't know, just it is a good model. Medicine doesn't work like that. We cannot. And there are many applications that are pushing towards interpretability and explainability of models. So the idea would be something like this. Like today we have some learning processes that get some learned function. You can call it neural nets. You can call it any model you like. Then you have an output, and then you have no way of understanding why the output was given, or debugging this model, or knowing any property of the model. And particularly in neural nets, it's hard to prove things with them. Do verification, for example. And the idea for tomorrow would be to have an explanation interface so that the human that's presented with the output of the model can understand why the model made that decision. Not just the decision, not just why something is risky, but because. Okay, so DARPA presents three approaches to this. The XI project of DARPA presents three approaches to this. One would be deep explanation, that is training the neural nets or deep models in a way that they can also learn explanation for the model or for the output. This is an interesting approach, but you still don't understand how the explanation is trained. So you're like trying to solve a problem with the same problem. You are reintroducing the problem into the training phase. The other way would be interpretable models, to train models that are a priori interpretable. That's a good approach, but it has some limitations, at least in our domain. So we resort to model induction. That is, we have a model of a domain, and we resort to extract a more interpretable one. Okay? We have a neural net, and we resort to extract some easier to understand models. In this approach, in model induction, we have two ways of doing it. You could do it by looking into the internal structure of the model, for example, looking into the internal structure of the neural net, or not doing that. If you do look into the internal structure of the neural net, you are really dependent on the architecture. You are really dependent on, for example, if you look at recurrent neural networks, you're really dependent on the size, on many things that describe its state, and if the problem was solved with a similar architecture or a different one or a more complex one, then the techniques that you may have will not work. So we resorted to treat the network as a black box, which means we do not rely on the internal structure of the network to make such model induction. To be more concrete, our problem is centered in symbolic sequence classification, which means we have neural nets, artificial neural networks, ANNs, that are trained to recognize sequences of symbols, okay? And we resorted to extract automata from them, because automata are a visual model and they're easier to interpret than a neural net. Okay, so this is called regular inference, and as I said, why it is a visual model, and it also enables formal verification. We may discuss that point a little bit later because there are some research questions regarding that. So a sequence, for example, could be, I don't know if you can see well because it has like low definition, but you can have a sequence of C, C, X, Y, A, B, D, and label it as label 1, and another sequence of the system could be labeled at label 2. It's an abstract interpretation, but you could think as, for example, actions in a kernel and label them as abnormal or as normal, for example. And a neural net can be trained to do that. So, as I said, we're working with neural nets that recognize symbolic sequences. And we resorted to do regular inference, which means extract automata from those neural nets. Please stop me if anything is not clear. I'd rather explain it at the moment than wait for the end of the...
Just a question.
Yes,
the
please.
sequence that you analyze, this is only string. This is not more complicated objects.
No, not at the moment. They could be more complicated objects, but you would need to have an encoding as a symbol.
Okay.
So imagine you have some continuous sequence, you would have to quantize it and have some symbols to represent it.
Okay, okay.
So, well, we have the network and we want to extract an automaton. We have the network, that's a good classifier, we want to extract an automaton. Okay. Regular inference, Anglin's regular inference, L star is the algorithm she proposed in 1987, and it's an active learning approach. Do you know what active learning means? Okay. So, the state of the art nowadays, when we talk about machine learning or we talk about deep learning, many scenarios, what they do is they have a bunch of data, and from this large amount of data, you try to infer some model. You infer a model to recognize, for example, cats and dogs. This would be the first approach. You have the world that has some data that is supposed to be a good representation of the original distribution of the data. Then you have a passive learner, and then you output a model classifier. The idea of active learning and the idea behind this algorithm is that you have the world, but you have a learner that's able to make queries to the world. So the learner is able to interact with the world, and when having some responses, it's able to adapt its model until some criterion of equivalence or probability property, and then you output a classifier. It's similar to reinforcement learning, where you have an agent that interacts with the world and learns some function over the world or the environment. So to be more precise, L-star algorithm says that you can learn an automaton from the world or from a teacher that exposes two interfaces, a membership query and an equivalence query. And what the algorithm says, and what you have to do if you want to program it, is to ask a number of membership queries and fill an observation table. At some point, this observation table will be consistent with an automaton. So then you build your automaton and ask the teacher if the automaton is the same as the one the teacher knows, because you work under the assumption that the teacher knows the automaton. Then the teacher may tell you, yes, this is the automaton, and then you have learned the automaton and you are happy. Or the teacher may say no and give you a counterexample. If the teacher gives you a counterexample, you then have to adjust your observation table and continue doing membership queries until you reach again an observation table that is consistent with an automaton and can compare it again. Given that what you're trying to learn is an automaton, the algorithm is proven to stop, to terminate, in a polynomial amount of time that's related with the number of states and the symbols of the language. Okay? So you will end up with the original automaton that the teacher knows. So using this framework or this learning process proposed by Anglin, what we did was, well, we substituted the knowledge of the teacher. So instead of having the automaton now, the teacher inside has the neural net. This seems like a good idea, but it brings with itself two problems. First of all, neural nets are proven to be Turing-complete models. Not every neural net, but the recurrent neural networks and such are proven to be Turing-complete models. So you might be trying to learn a hypothesis that is not representable by an automaton. You may be trying to learn something with a hypothesis space that doesn't contain the target concept. And the other problem is there's no such algorithm to compare an automaton with a neural net. So these two problems of equivalence and expressivity, how do we tackle them? Okay, we did two things. We used the PAC framework, PAC, probably approximately correct framework. That's a framework proposed by Valiant in theory of the learnable. And we set a bound to complexity, such as we stop at some point when the automaton we're proposing reaches some complexity. Because as I said, we use an iterative approach to learn the model, so every step we make, we are making the automaton more complex. So we decide to put a bound on that complexity in order to be able to stop at some point, because the algorithm doesn't guarantee that. What is the PAC framework? Does anyone here knows the PAC framework? Okay, I'll quickly tell you about it. The PAC framework is made to compare two models, such as you can have an approximation of one can be an approximation of the other one, and you have some confidence over that. So you can say that two models are, for example, you have this concept, this would be the neural net, and you have the hypothesis that would be an automaton. And you can say that if the probability of an element belonging to the symmetric difference, that is, that the element is in the neural net and not in the automaton, or belongs to the language of the automaton and not to the language of the neural net, if the probability of an element belonging there, so it would be these places, that's just the hypothesis or just the concept, is below some epsilon parameter, then you can say that those two models are epsilon good approximations. Okay? If, for example, the probability of any of those elements is lower than an epsilon, then you can say that those models are epsilon good approximations. And if you can say that with a confidence that's higher than 1 minus delta, then you are under the probably approximately correct framework. Sorry. How do you test that? Well, in order to test that, you resort to doing sampling. You get a sample of a size that's proposed by the framework. That's a function. The size of the sample is a function over epsilon and delta. And if every element on the sample is not in the symmetric difference, so if both models classify every element of the sample equally, then you are with a confidence that's higher than 1 minus delta. You have with a confidence that is higher than 1 minus delta, two approximate epsilon good approximations. Sorry. Okay. Is it more or less clear?
So the idea is that the sample is has probability as a set greater than 1 minus delta over
the idea is that
over the universe.
No, the idea is that that if this sample is consistent in both models, then you have this confidence that the two models are epsilon good approximations. So the size of the sample is calculated in that way to guarantee that if every element is classified equally by both models, then you can have this confidence, a confidence greater than 1 minus delta, that the two models are epsilon good approximations regarding some arbitrary distribution. Okay? And that part, the part of the arbitrary distribution, we can talk about it later, more research questions and lines. So, if we are presented with a sample which says is R, that's a function on epsilon and delta, and every element of the sample is classified equally by both models, for example, this element here that the automaton would say is not a good element and the neural network would say the same, or this element here that the automaton would say this element belongs to my language and the neural net would say the same, then we can say that those models are epsilon good approximations and that we are pretty confident about that. Okay? Yes?
So that's one question. So what is the relation between epsilon and delta? What is the relation between epsilon and delta?
There is none. There are two parameters, so you have to set them.
Because basically the epsilon here is visible, right? So you take the part of the hypothesis and the concept that are not overlapping, and this should be the probability of x should be
Yes.
smaller or equal than epsilon, but the delta is not defined through visually what you have.
No, it isn't. Would mean that if you did this sample a bunch of times, you would get this approximation,
Right.
the 1 minus delta times or more.
There is a relation between the two. So
There's not a relationship they're like orthogonal probabilities. One is how much the models approximate, and the other one is how sure you are about that. So there's no relationship between them. You can define them with different numbers and have different results. So yes, and the second one is really hard to visualize and to test.
What would be the domains of the hypothesis and the concept?
You
are talking about sets, but what
This-
are
this-
actually the elements there?
It could be anything. In this case,
Yeah.
would be sequences.
Okay, so both are infinite.
The sets, yes. Yes, you're comparing infinite sets, yes.
And how do you know that how do you choose the data sets so that you can say that actually you have that probability?
You are sure about that over some arbitrary distribution. So how can you choose a good distribution that would mean that you're learning well? I don't know. I've been talking with an expert on distribution over languages today, and he has I don't know how many years of work on this, and it's a good research question too. Yes. Sorry, sorry for not being able to answer every one of your questions. Okay. The PAC-PAC framework is okay, but as we are working with some more expressive model, we're trying to learn some more expressive model, there's this problem of we may always end up finding a sample that's not fully consistent. That's not the green sample that we've seen. So what we did was propose an extension to the framework to get a size of the sample that would allow some errors. Some that would allow, for example, some of these black dots, k black dots, And well, it's everything. It's written on the paper. There's a lot of mathematical stuff there, but the thing is, it is hard to compute.
Sorry, I have a stupid question.
No. There's no stupid question. Okay. Delta is the confidence you have over the two models being approximate, being epsilon good approximations.
It's not related to epsilon.
It's not.
Does it depend on the number of samples you take?
Indeed, delta and epsilon are parameters. What depends on the number of samples you take is R. R does depend on the number of samples you take. Because as you do many iterations of this algorithm, you need to adjust the size. You do, yes. Indeed, epsilon, the size of R is a function of epsilon delta and I being I the number of iterations. So, yes. So we propose an extension, and what happens is that it's hard to compute. It's an optimization problem that it's not that easy to compute. So the idea would be to have an extension that when you do the sampling, you have you allow that the intersection of your sample and the divergence space, the symmetric difference, would be of some size lower than k. But it is not easy to compute. So what we ended up doing was running tests over the PAC framework, and when we reached some complexity bound, which means we didn't pass any test, but the model we are proposing is too complex, we resorted to calculate what I would call a residual approximation parameter. That means that with confidence delta, we have some approximation. We cannot have a guarantee over it, but we can have a measure of it. We measure the approximation given that we weren't able to reach the desired approximation during the computing time we allowed.
Sorry, I have again a question.
Yes, please?
K, this is a set or an integer?
It's an integer.
So, okay, so
Yes, it's a size.
The number of elements in R.
Yes, it's the size of the intersection.
Okay.
It's okay? It's okay? Okay.
So
Yes, maybe the notation is
finite.
eh?
So the sets are finite.
For sampling, yes, but the theoretical test sets aren't.
Okay.
So we're resorting to some distribution
Okay.
and doing sampling over them to compare two theoretically infinite sets. Yes. So it would be, yes, I would like to have another way of comparing the sets. So if anybody has an idea, please. And then we used many examples, but most interesting one maybe was an e-commerce model. We got an e-commerce workflow that represents the way of function calls between the system of the e-commerce. So we trained an ANN with data from this model, and we ran several learning processes. A learning process is a complete run of the algorithm, which means that the algorithm proposes a series of automatons until it reaches a bound or passes the sampling test. So we did that 20 times in this case. And the results, okay, this would be an image of the model. It's pretty simple, I would say, but it's okay. It has a lot of symbols, and these are abstractions of open session, ending session, adding things to a shopping cart, and such. And we proposed some epsilon delta that are the same, but there's no need for them to be the same. In red, we have the proposed epsilon. In black, we have the residual epsilon. And in blue, what we have is a measured error. The error, as we called, is an error that we measured on a new data set, okay, that's independent from the learning process. And what it does is measures the difference, the number of elements that are classified differently by both models. And in every case, And in every run, and that happened for every experiment we ran, the measured error was below the proposed bound. I mean, yes?
Just clarification.
Yes, these are six different automatons that were reached during the learning process. 20 learning process reached 6 different automata. Sorry.
If I understand correctly, you took traces from the e-commerce application and then
Yes.
Trained a neural network to
Yes.
recognize
Yes.
traces from non-traces.
Yes.
Can you just say a little bit about that neural network that you trained?
It's an LSTM with, I think, it's one or two LSTM cells, and then it has a simple perceptron layer and softmax. I think yes, softmax. It's a 2 class, but I think we still use softmax, and it reached like a 96 or 99% of accuracy. It was pretty well trained. I mean, maybe overfitting.
And so you generated true
Yes.
traces from the known automaton, but how did you generate?
We use a uniform sampling over the length up to some size. That would be the size would be 2 times the number of states of the automaton plus 1, something like that. This number was chosen because RMPI, it is a well-known regular inference technique to learn from passive to do passive learning. So you learn over data. So we choose a number of sequences similar to the one that this common algorithm requires, and then we train the neural net with that.
And just so I understand again, so in terms of the traces that are output by the
Yes.
automaton, it's a very non-uniform distribution over
Over the length.
strings, right?
Over the length.
Well, over all the strings, right? Some strings are much more likely than others, right?
Yes, but you can do yes.
Okay.
But we
I just
didn't.
wanted to understand.
Okay, yeah, I mean there are many ways to do this sampling over the automaton. We just choose a very naive one, but there is some work on that, but we didn't resort to it.
To sample the automaton, you turn it into sort of a Markov chain, and you let it run and emit symbols?
No, because we needed positive and negative, so we did sample over epsilon over sigma star, and then we classified it with the model.
Oh.
It was really more simple.
But you are training a neural network.
Yes.
And so I do not understand how you can derive an automaton from the neural network.
By asking queries to it.
Okay.
We just put this neural net inside a teacher.
Okay, maybe my question is more related about what is inside this automaton. Because once you have your query, you have the results of these queries.
Yes.
How do you know I have to add some steps, some transition at this place?
That is part of the build automaton method of the algorithm. What you do is you have a table with prefixes and suffixes, and you have which prefix and suffix, if they belong, if the whole string with the prefix and the suffix belong, and that lets you infer number of states and which states go to which state. It's an algorithm that works really similar, I would say, as automata minimization. It works in a really similar manner.
Okay.
Okay, so is it all more or less clear? Okay. And then we got another test sample, and what happened was every measured error was below was below the calculated residual approximation parameter. So the residual approximation parameter is seems to theoretically hold. And so, as conclusion, we could say that we managed to do black box irregular inference over artificial neural networks. We proposed two complexity bounds to the L-star learning process that worked. I mean, when I say worked, I mean that when measuring the results and giving some and calculating the approximation, it was consistent in the empiric results. And we proposed an extension and an analysis that would be the epsilon star, the analysis, the extension would be all the previous part for non-pack conforming models. And for future work, there's a lot because many questions you asked could be part of future work. And one thing that would be really interesting is reducing the variance of the learned models, because it is not good to have 20 runs of a learning process and have 6 different models for 20 runs. But it's all due to the sampling. It's all due to the random sampling and the way you choose counterexamples. We had done some work on that, but we didn't get much out of that. So that's it. Thanks for listening to me. Yes, please.
Sorry, I asked many questions, but
no,
your topic
perfect.
is very close of mine. I was wondering, can you learn something when the string is very noisy? For example, you have a letter which occurs significantly more often than the others. Because I fear that it will kind of bias your neural network. It will always predict this letter which occurs very often. And so are you able to learn an automaton in this kind of situation?
We are, okay, let me see if I understood. You have this problem where there's some letter that occurs very often?
Significantly more often than the other one.
So, but what is the problem? You have many sequences that happen to be like that over the whole universe?
Assume that you have a single string where the most of time you have always the same letter and sometimes not.
Mm-hmm.
So can I learn something in this kind of situation, or I will just output the automaton will predict always the same letter? You see what I mean?
What we are doing is automatons that recognize words, not a specific symbol. But maybe you have to reformulate your question, because I may not have understood
Maybe
it.
I was not clear. Suppose that your string is A, B, C, A, B, C, A, B, C, for example. I fear that because A is highly likely to occur, you might be happy with an automaton which outputs only A.
Maybe that is the case. Yes, that depends that depends on two things. First of all, how you train the network, and secondly, what distribution you choose to learn over. Mm-hmm. Maybe you have a distribution that doesn't happen to really represent or choose representative words of your domain. Then maybe the two models are approximate given that badly chosen distribution, and then this framework would be happy with that. So yes, the how to choose the distribution over sigma star is one of the problems of this approach. But there's no way of knowing. You can approximate it. Okay, then we can talk about.
No question? I have one.
Yes?
So you train the neural network?
Yes.
So you have like data from e-commerce?
Yes.
You encode that as a sequence?
Yes.
You train the neural network with that?
Yes.
And then to train the automaton, you said that you uniform sample sigma star.
To train the automaton.
To build the automaton.
To build the automaton, we used L-star algorithm.
Yeah. But the data, the queries.
The queries.
Yeah. How, like, if you actually random sample like the space of sequence, you might have queries for which you don't really know the answer. So
Sure.
you know what the neural
Yes,
network
yes.
answers, but not what the real.
Okay, there are two things. First of all, the algorithm does not do random sampling. The algorithm chooses what to ask in a smart way. What the teacher does is do random sampling to compare and tell, well, the automaton you're proposing is equal to my net or not. But the algorithm of L star has a concrete way of choosing what to ask.
Okay.
Second, the neural net is trained, so it will output something. Maybe it's not right, but it will output something. And you can make a decision over that something. It will output an array of probabilities over your classes, and then you can choose the maximum of between them. Maybe the neural net never saw that concrete sequence. But nobody knows that unless you really know the training data.
Okay.
So yes, it's a matter of trusting. Well, when you work with machine learning, that's the idea. The idea is that when presented with new data that the model has never seen, it will be consistent with the whole distribution of the data that the model was presented with. That's.
Okay, and last question. When you show the plot with the epsilons,
Yes.
you said something like epsilon equals 0.
Yes.
0.05. That
Yes.
means that that's the amount of the percentage of cases that both things said different things, and like 95% of the time, both the automaton and the neural network agreed on the label.
That was the idea that the target of the algorithm. But okay, I'm gonna go back, please.
Maybe you can use the.
Yes. Okay. That would be the ideal. Okay, but after learning and stopping, we for each automaton we did this epsilon star calculation. That's not dependent on the iteration, so it indeed can be lower than the original target one. So we say, okay, I wanted to learn something that was as much as this wrong. This could be the number, the percentage of divergences. Okay. So for example, we learned this B automaton that has five states. And we measure this epsilon star. That would be, okay, I did a test, it has some errors, but the residual error would be up to this. It's lower, and then we measured it, and in blue is what was measured in test. Okay. So indeed, we tried to learn up to this, but we learned better, indeed, and when measuring it, it was better. Under this arbitrary distribution. That is how to choose the distribution.
So you never run the automaton with real data?
With a real domain?
Yeah.
Rather than
to train the neural network.
Eh?
With the one you used to train the neural network to see if it outputs something similar.
No, we didn't run it on the training data of the neural net. No.
Okay.
Is it obvious that the automaton is more explainable than the neural network? It doesn't seem so clear to me that you tell your cancer patient, we've got this automaton that says you've got cancer.
Well,
we would be happier than if he said it was
there are many questions there. The cancer patient and the automaton being more explainable. Well, metrics for interpretability. That's another research question. The conference I was in Hamburg, someone was doing some metrics for interpretability of models, but they were kind of model agnostic, but not at all. So model agnostic metrics for interpretability would be a really interesting research line. We work under the assumption that having a visual model is better, is more interpretable. You have some people like shouting, yes, visual is better. That's one assumption, and maybe there are some domains it's not that good. And in the medical domain, well, that depends on what the training data was, because if you're using an image and trying to classify if someone has a tumor over some brain image, this is just for symbolic sequences. It's not for that.
No, it's just a
There's
example.
There is some work on that. Maybe you can. Let me see. What was it called? Taylor. Oh, I look for it. There's some interesting work on explainability of images. That's really recent. I can show you later maybe if you want. So, any other question?